All right, folks, it is time to introduce the trigonometric identities that you are going to be using all the time when you get to calculus. So, in this section, the goal is to simplify these identities and verify these identities. When we say verify, it essentially becomes a proof. And so, you may have done this in high school with geometry. I want to point out it's going to look very different. And if that is something that you didn't enjoy, fear not. Like, it does look very different and it is a very different process. Okay. So let's start by writing this identity in front of us in terms of sine and cosine. We want to simplify it as much as possible after that. So I know I can go ahead and rewrite all of these. So I'll go ahead and zoom in so I have plenty of room. So I can say 4 times sine of theta over cosine of theta, because I know that tangent can be rewritten as such. And I also know secant is 1 over cosine theta, and cosecant is 1 over sine theta. Okay, so now I've rewritten it. From there, I need to figure out what goes together, what might cancel, all that good stuff. So I think I'm going to go ahead and work with this right-hand side. I have 1 over cosine theta times sine theta over 1, right? That's what's going to happen when we have to divide a fraction by another fraction. And then we have 4 sine theta over cosine over here. And so on the right, things are going to simplify. So I'm going to have 4 sine theta plus sine theta all over cosine theta because we now have common denominators. Okay, now that we've done that, we can combine the 4 sine and the 1 sine. Whoops. And we're going to have 5 sine theta over cosine theta. Now, what we have written here is equivalent to what we have written above. We have just written it in a way that looks different and is simplified as much as possible. Okay? We're going to do more of that in the next few pages. But first, there's also a bunch of identities that you really need to start getting familiar with. Some of them we've seen, some of them are going to be new. For example, the periodic identities are no longer new. We've now talked about all those. Sine and cosine and their reciprocals all have a period of 2 pi. So we know that for cosecant and secant, we could have any amount of loops around the circle of 2 pi, whereas tangent and cotangent have a period of pi, so it'll be pi k instead. Okay. So those are from earlier in 8.1 and 8.2. Then we have the even and odd identities. So Sine and cosine and secant are the only ones that when you put a negative input in, you still get a positive input out. Whereas sine and tangent and their reciprocals, you can essentially bring out that negative to the front. That's going to be the case for all of these guys. Okay. All right. If you can hear my cat in the background, I'm sorry. He has decided now is the time to chat. Um, He just wants everyone to know he's here. We have reciprocal identities. You have now heard about those. So those are quick to plug in. Secant and cosine or are go together. Sine and cosecant go together, and tangent and cotangent go together. Okay. Then we have the Pythagorean identities. Now, I am going to do a little bit of math here to show you how we end up with getting these. There are 3 versions of the Pythagorean identity. Um, they are going to be tangent squared theta. Whoops. I'm pretty sure everything I just wrote down deleted. Yeah. Um, tangent squared theta plus 1 equals secant squared theta. And we have 1 plus cotangent squared theta equals cosecant squared theta. Now you're like probably wondering, how do you know? How do you get there? All that stuff. So let me show you. If I start with sine squared theta plus cosine squared theta equals 1, and I decide I want to divide by sine squared theta everywhere, something's going to happen. Okay. This is going to turn into a 1. This can be simplified as cotangent squared theta, and this can be simplified and written as a reciprocal cosecant squared theta. Okay. That's what got us this guy. We can do the same thing if we were to divide everything by cosine. So I'm going to come down here, dividing the original by cosine yields this version. Okay. I encourage you to do that just to do it on your own paper to see it happen. Okay. Um, that way you are familiar with how those operate. And finally, we have the cofunction identities. We have already talked about those. Okay. Sometimes you have cosine and want to find sine, but you don't necessarily have one or the other. So you're able to use the cofunction identities. Okay. And I'm just going to rewrite these down since they did delete. Okay. Now, all of these are going to be pretty useful. Okay. When we need to simplify or verify an identity. So let's go ahead and start with A. Simplify as much as possible. So here's the thing. There are 1.5 million ways that you could approach these types of problems. My general suggestion is to get things in terms of sine and cosine and then start trying to get rid of stuff. So that's what I'm going to do in this case. I know that cotangent can be written as cosine of x over sine of x. Then we have cosine of x plus 1 over sine of x times sine squared x. I immediately notice that the sign on the far right will simplify down a little bit. Okay. So I'm gonna have cosine squared x plus 1 times sine squared x all over sine of x. Okay. I'm not going to simplify yet, even though I know that that could happen. This one really becomes irrelevant, so I won't even worry about it. And I immediately notice that this right here is a Pythagorean identity. So I'm going to go ahead and rewrite it as 1 over sine of x. Or we could simplify even more and write cosecant of x. This would be the simplest form. Okay? It doesn't require us to use sine and cosine, so I would write cosecant of x as the simplest form. No fractions. Okay. These are tricky when you are first working through them because you aren't quite familiar with the identities. The more you practice, the easier it's going to get. And sometimes they really end up being fun because it's a bit of a puzzle. Let's look at this next one. Immediately looks more complicated. I think the best place to start is to figure out which of these are even and odd and what happens with the signs. Okay. So we talked about earlier on the previous page that cosine and secant end up being able to ignore the negative. So we can ignore this guy, and the next one is positive. So really, I can just go ahead and rewrite this first part as 4 cosine cubed y times secant of y plus 3 sine squared y minus sine y times, and this one we're going to have to bring that y negative out. Whoops, I didn't mean to write the y. The negative out, and we'll have sine y. Now let's simplify and combine like terms or rewrite things in terms of sine and cosine. My first term is not going to change, so I'll bring him down. So 4 cosine cubed y. Secant I can write as 1 over cosine y. Then I can add 3 sine squared y, and these two will combine and become positive sine squared y. I can continue combining like terms. On the left, if I combine, I'm going to have 4 cosine squared y, right? The cube and the cosine on the denominator will go away. Here, I can combine like terms and I have 4 sine squared y. Okay, notice these now have a 4 in common. I might take it out. Cosine squared y plus sine squared y. Okay. I also recognize that this is a Pythagorean identity again. That is equal to 1. So after simplifying, I end up with just 4 as my answer. And that is fine. That is totally fine. That can happen. Okay. Pythagorean identity. Okay. Now, if we want to write this completely in terms of sine and cosine, I'll go ahead and start by writing cotangent and secant in terms of sine and cosine. So I have cosine squared of negative theta over sine squared of negative theta plus 1 over cosine theta over sine theta. Now I think it's time to move those negatives out or ignore them completely. For cosine, we can ignore it. For sine, we can bring it out to the front. We can bring down the rest, or actually we'll go ahead and simplify. So 1 over cosine over sine is going to be 1 over cosine theta times sine theta. Okay. Now I'm thinking about what else can I do? Do I need to get some common denominators? What makes the most sense? I see that I have um I see that I have two parts of this that are still written as cosine. So now might be the time to rewrite that. So I know about my Pythagorean identity. So I know sine squared theta plus cosine squared theta equals 1. So if I rewrite this as 1 minus sine squared theta equals cosine squared theta, that would help me rewrite cosine squared theta in terms of sine. So maybe that's what I'll do here. Okay. Then I also am thinking about, okay, well, I also need cosine theta. So if I know that 1 minus sine squared theta equals cosine squared theta, if I take the square root, 1 minus sine squared theta, that would give me cosine theta. In this case, there are technically two solutions. Let's just go ahead and take the positive solution. We'll make that decision there. And that could replace cosine theta. So then my final expression that I could write would be 1 minus sine squared theta over negative sine squared theta plus 1 over sine theta times the square root of 1 minus sine squared theta. Now, I'm not saying that this is better than what we were provided. Obviously, it looks more complicated, but ultimately, the goal of this problem is to just get familiar manipulating these types of questions. Okay. As long as you're comfortable manipulating, you're going to be totally fine. Okay. It just takes a little bit of practice. Now, when it comes to verifying, there is a difference between solving and verifying. Solving means you're looking for a solution. You're looking for x equals something. When you're verifying, you're just trying to prove that that expression is actually correct. Okay. And so you did this in geometry, most likely in high school. It may have been something that you didn't particularly enjoy or it didn't seem to make sense because it was very conceptual. But here we're going to use these identities from the front, which I know some got erased, um, to actually confirm that yes, this is correct. This actually breaks down into a trig identity. Okay. There's a couple different strategies. I'll talk you through kind of the way that I approach it. Because I've found certain methods are more convenient than others depending on the scenario. Okay. Let's start by verifying tan theta times cosine theta. Suggestion number one, start with the more complicated side. That would be this side right here. This side has more stuff going on. So this is the side that I'm going to work with. I'm going to go ahead and write everything in terms of sine and cosine. So now I have sine theta over cosine theta, all times cosine theta. Okay. I'm noticing immediately that these cosines are going to cancel out, leaving me with sine theta. That does, in fact, equal what we had above. So, yes, that works. When you're done with the verification, you could do a check mark, you could do a smiley face, you could circle it and say, this is it. If it's a Pythagorean identity, you could write Pythagorean identity. There's a lot of ways to say, like, hey, I figured it out. Okay. Let's look at this next one. Right out of the gate, I see the left side. The left side looks complicated. I'm going to go ahead and work on that negative x. That negative x can come out, and it'll be 1 minus sine of x. Okay. This is going to be a foiling situation. I'm going to have 1 plus sine of x minus sine of x minus sine x squared. Okay. Now, I went ahead and wrote all of it to show you this, but that's going to cancel out, and I'm just left with 1 minus sine squared x. Okay. I know that that is equal to cosine squared x because of the Pythagorean identity. And if I look at this guy over here on the right, that's also cosine squared x because it's a reciprocal. So that means these guys also match and we verified the identity. Okay. You could have also even stopped here on this row and said, hey, this is the Pythagorean identity, right? You could have stopped there. You could have gone one step further and shown that their cosine squared equals cosine squared. Either of those is an appropriate stopping place. Okay, let's keep going. They're going to get a little bit more complicated, okay? But as you practice, they do start to come together. Now, like I said earlier, start working with the more complicated side. So that to me says this guy over here. There's already a lot going on just looking at that. So I'm going to go ahead and say sine of x over cosine of x minus sine of x over 1. I'm going to go ahead and make everything a fraction. All divided by sine of x over cosine of x times sine of x over 1. I think I'm going to need some common denominators for the top. So the top is going to get multiplied by cosine. Okay. So I'm going to have cosine x and cosine x. Okay. Now I'm going to combine what I can. I'm going to have sine of x minus sine of x times cosine of x all over cosine of x, all divided by, so this is the bottom half, sine squared x over cosine of x. Okay. Now, both of these fractions are being divided by cosine. Okay. That is worth noting. So they are going to end up canceling out. So I'll go ahead and simplify. I know they're going to go away. So now I have sine of x minus sine of x times cosine of x, all divided by sine squared of x. I immediately notice that all of these have signs. So I'm going to divide out a sign on the numerator. So dividing that out, factoring it out, I'm left with this in the numerator over sine of x. Okay. When that cancels out, okay, make sure I haven't missed anything here. Oh, I have missed something. I missed my square. There it is. Okay, when this top part cancels, the bottom cancels out with the square, so you're only left with one sign instead of squared sign. So I'm gonna have as my final answer 1 minus cosine of x all over sine of x. Now, you may have forgotten there was another side of the equation, but look at that, it does match. So we have verified that the right side does equal the left side. Okay. And now we do some more practice. All of these are going to be true, so they should all somehow work out. Again, I would recommend starting with the more complicated side, and after choosing a side, write everything in terms of sine and cosine. So we'll go ahead and start that with A here on the left. We have sine squared x over cosine squared x all over 1 over cosine squared x. From earlier, like I said, the denominators will cancel because they're the same. And so you're immediately going to be left with sine squared x equals what we started with. So yes, that works. Taking a look at this next one, you could really start on either side. I'm going to start on the left. To me, the left looks more complicated because it's adding and not multiplying. So I'm going to start there. I again want to remind you that there are a million different ways to start these problems and work through these. It's just a matter of what are you most comfortable with. So we'll go ahead and start by writing sine over cosine and cosine over sine. Okay. Now I'm thinking I probably need some common denominators. So the left is going to get multiplied by sine. And, and the right is going to be multiplied by cosine. Okay, the nice thing about that is now we can write this as 1 over sine x times cosine of x, okay, which is also equivalent to cosecant, whoops, of x times secant of x, which if you look back up here, that is what we had at the very beginning, so we have verified. Okay, taking a look at the third one. Okay, the third one is a little bit tricky. The third one took me a few minutes to work through the first time around. So don't get frustrated if you don't get it right away. If you're kind of getting stuck, just take a moment and go back to the beginning and say, hey, did I miss something? Or is there an easier way to do this? Okay. I even have moments where I'm not always right on the first try. Okay? So let's go ahead and write the left side. The left side is definitely the more complicated side. So we'll write it in terms of sine and cosine. So we have cosine of x over sine of x divided by cosine of x over sine of x plus sine of x over cosine of x. There's a lot happening here, and so my instinct is to multiply everything by the denominators I need. So sine and cosine. So I'm going to multiply by sine of x over sine of x, and I'm going to multiply by cosine of x over cosine of x. That way I'm hitting all my bases and I can immediately eliminate some stuff. Okay. I'll start with sine of x. If I multiply by sine of x, I am going to end up with, let's see, cosine squared in the numerator. Okay. Um, because when I multiply cosine and cosine, that's also gonna go away. And then if I multiply by sine of x in the denominator on the left, I'll be left with cosine squared because of the other cosine that we multiply by. And then if I multiply by sine and cosine for the bottom right, I end up with sine squared x. Okay. So a lot of stuff ends up canceling. Now, if I'm looking at this, I think, okay, I know I have cosine squared over cosine squared and cosine squared over sine squared. Okay. Now, I know that this right here is a Pythagorean identity. So I could rewrite that as 1. I could write cosine squared x over 1, which is just going to be cosine squared of x. Looking back at the very beginning, that's what I started with. So we have officially successfully verified this identity. Okay. Taking a look at D, this one really might not have a more complicated side, right? This one could be bad all around. So maybe something that you can do is cross multiply because you do have an equal sign between these. Okay, so maybe cross multiplication is the move for this one. So let's try that. I'm going to have negative cosine theta equals 1 plus sine theta times tangent theta minus secant theta. That doesn't really look much better, but let's just see what happens. Okay. Um, and I'm going to go ahead and distribute everything on the right. So that's going to be negative secant theta. Whoops. I don't know why I just wrote that. I'm just doing all out of order. So tangent theta minus secant theta plus sine theta tangent theta minus sine theta secant theta. So there's a lot happening, okay? I think now is a good time to simplify and write things in terms of sine and cosine. So we have cosine, oops, sine theta over cosine theta minus 1 over cosine theta plus sine theta times sine theta over cosine theta minus sine theta times 1 over cosine theta. Okay, I'm immediately noticing all of these have cosine in the bottom, and there's a lot of sine on top. So let's just keep going. I have sine theta minus 1 over cosine theta plus sine squared theta over cosine theta. And I have sine theta over cosine theta. Okay. Now I can multiply everything on the left by cosine theta. So I would have negative, oops, cosine squared theta equals sine theta minus 1 plus sine squared theta minus sine theta. Okay. I notice that this and this will go away. Okay. I'm left with the Pythagorean identity. Although it doesn't really look like a very pretty Pythagorean identity, it is correct, right? If I bring the 1 over and I bring the cosine squared theta over, I do have the Pythagorean identity. So we have verified that. There's a couple different ways to do this. You did not have to cross multiply. Theoretically, you would end up with the Pythagorean identity either way. Okay. So if you want to try it a different way, feel free. I am not expecting a certain method as long as you are using the identities correctly. Our last practice problem uses one of the last identities. So here we are going to use sine of x. Okay, here we're going to use sine of, whoops, cosine of x over sine of x times cosine of x plus sine of x. Okay, so that's all going to multiply. Before we multiply, let's go ahead and rewrite this as cosine squared x over sine of x plus sine of x. If you're already feeling comfortable, you already know what's about to happen. If you're not, you're about to find out. So when we distribute, we're going to have sine of x times cosine squared x all over sine of x plus sine squared x. Okay. You see that the sine is going to cancel out. You're left with cosine squared x plus sine squared x, which is equal to the Pythagorean identity. We have verified this identity. Practice these. They are worth taking the time to practice. Being comfortable with these identities is so important in calculus. It is one of the most important concepts that will be needed. Okay. And it's one of those things that a lot of the time our professors are going to assume that you have gotten those down. Okay. So please, please practice these.